All right, how we doing, folks? This is the last set of notes and the last set of videos for the semester. You can probably hear my cat yelling. He's not happy right now. In any event, folks, let's get into it. Okay, here we go. Great. So, we're going to get into this final module on spectroscopy and all forms of electronic spectroscopy. And by electronic spectroscopy, what we really mean here is spectroscopy dealing with the electronic energy levels. So transitions of electrons from lower lying states to upper lying states. Okay? And we shall see how in some forms of electronic spectroscopy, depending on the resolution of your spectrometer and the phase of your material, the rotations and vibrations of molecules can also be intimately coupled with the electronic transitions. Okay? You're going to have to listen to my cat. I don't know if that picked up on the microphone. He is not happy right now. Anyways, so the first type of spectroscopy that I want to introduce is photoelectron spectroscopy. Okay, so this is based off of the photoelectric effect. This is one of the very first things we talked about this semester. And if you recall, the photoelectric effect is based on this notion that we can use light to photoionize a sample. Okay. So typically we deal with, well, always with solids in XPS. Some more recent techniques have shown how you can do liquids on photoelectron spectroscopy, but it is not straightforward. And I'll talk about why we typically do solids in photoelectron spectroscopy. Okay. So if you recall, if you shine light with a certain frequency, that frequency has to be sufficiently large enough to induce photoionization. Okay, so for example, if you shined red light, 700 nanometer light on potassium metal, nothing would happen. It's not enough energy to ionize the potassium. Okay, so but if we look at what the work function phi, which if you recall, that's the energy required to remove an electron, energy to remove electron. The work function for potassium is 419 kilojoules per mole. And if we were to convert that 419 kilojoules per mole into a single joule per molecule, okay, we could use this idea of that energy being quantized. So H nu, I could come up with a specific frequency for this work function. And if my incident radiation, so I'll point here, if my incident radiation has a frequency that's larger than the frequency of the work function, then photoionization will be induced. Okay, so if we look at that in a little bit more more specifically, okay, so here we can see on an energy level diagram, here is phi, our work function. Okay, sometimes this is also referred to as the binding energy because it's the energy required to remove an electron. And so this is kind of showing you that example that I just showed here, where if we suppose H nu here is 700 nanometers, you can see that's not enough energy to match the work function. However, if, for example, this H nu were 200 nanometers, and of course, assuming the same potassium example, you can see that 200 nanometers not only will be more than enough to induce photoionization, but the excess energy will result in the kinetic energy of the electron. Okay? So if we only use an incident radiation source enough to go to right at the work function, okay, that's called threshold ionization, and that will not result in the ionization of the analyte. Okay, so that will not result in the removal of an electron from the surface. But any energy just past that threshold will result in kinetic energy of the electron. And as you can see, that's what's given by this right here. Okay, so we're using some lamp and we're bombarding a sample. If that incident radiation has got a great enough energy to induce ionization, we'll get all of these photoelectrons. And those photoelectrons can be sent through what we call a hemispherical energy analyzer, which I'll show you in the next slide. And then those electrons' kinetic energies are detected. Okay. So as it turns out, if you increase the frequency of incident radiation, you'll see a linear increase in the kinetic energy of the photoelectrons. Okay. And so if you recall here, this value, this intercept, gives us the threshold ionization, right? Because if we backtrack all the way down here, you can see this corresponds to an electron with 0 kinetic energy, right? Which is exactly what you need for threshold. And as you increase the frequency of incident radiation, you'll get a linear increase in the kinetic energy of the electron. And if you guys recall from the beginning of the semester, the slope of this line will, of course, be Planck's constant, right? Because we have this very simple equation that just says, here's the equation. So it's a y equals mx plus b, right? Y equals mx, and I'll say y equals mx minus b because on that scale, the work function will go down. It'll cross the y-axis at negative values, okay? So you can see right there, the slope is Planck's constant, okay? So now my cat is like sneaking up and trying to attack me. This is hilarious. I might get slightly distracted from him. Apologies. Anyways, okay, let's move on. So here is an actual picture of an XPS device, okay? So for one, we note that, so what I've described up here is just generally photoelectron spectroscopy, okay? And of course, depending on the energy and wavelength of light, we will knock out various levels of electrons, such as either the valence electrons or the core electrons, okay? So specifically, X-ray photoelectron spectroscopy, or more commonly known as XPS, will ionize core electrons, all right? So here you can see is our Bohr model diagram of an oxygen atom with its various electron subshells, all right? And X-ray photons, as it turns out, are energetic enough to knock out core electrons, right? So you can see that in the case of oxygen, this is knocking out the 1s electron. So it's completely ionizing that electron. And this is useful because, as it turns out, those core electrons are really specific to chemical environment, okay? So just like in NMR, we kind of think of this as a chemical shift. Well, depending on the oxidation state or the chemical environment of our analyte, so in other words, is it an atom or is it a molecule? And if it is a molecule, is it a covalent molecule or is it an ionic molecule? So these very simple details are very sensitive to XPS. So the energies, the binding energies of these core electrons can be related to their chemical environment and molecular structure, which is really cool. And so XPS, as you can see here, so I'm kind of talking about these bullet points backwards. So it provides elemental composition analysis. So like I said, you can do elements or you can do molecules. And either way, what you end up getting is an elemental composition of your sample, all right? And also XPS is a surface sensitive technique. And so what I mean by that is if here is my analyte in question, okay, and let's just go back to that potassium metal example, right? Let's suppose this is K solid, all right? When this incident radiation comes in, specifically this X-ray, okay, photoelectrons are ejected. However, the only photoelectrons that make it to the detector are those originating from the surface. And when I mean the surface, I'm talking about a couple of molecular layers, right? So we know that some electrons will diffuse down into the surface and we never see those in the detector. So the electrons that make it out are only coming from a few what I'll call mono layers. So just a few molecular layers. So this is also really cool because if you're interested in this surface chemistry, which is most useful in catalysis or in environmental atmospheric chemistry, like stuff that I'm interested in, that molecular interface is really important, right? It's where the gas phase experiences the solid phase. It's where those two phases will interact, or where a liquid phase experiences a solid phase. So being able to probe molecular details of an interface is really powerful. Okay, so here we have a picture of an XPS device, and these things are complex, expensive, and difficult to use. And that makes them really exciting. Okay, so here we have the detector. So this big old looking hat, we call that the Hemispherical Energy Analyzer. So that's the Hemispherical Energy Analyzer. And I'll show you a better schematic in the next slide. Okay, our sample rests right in here. And typically there's a little window viewport into this vacuum chamber. So this entire thing needs to get pumped down to about 10 to the minus 9 to 10 to the minus 11 torr. So we call that UHV. That is ultra high vacuum. 10 minus 10 torr, roughly, okay? That is challenging, to say the least, to get a vacuum system to pump down to a pressure like that, okay? So here is the X-ray gun, and they're actually called X-ray guns. So most typically, it's an aluminum anode that has a lot of energy pumped into it, and that evaporates off electrons, okay? And so it's evaporating off electrons through this core shell interaction. So if we use, for example, aluminum, you typically hear this referred to as an aluminum K alpha radiation. And so K referring to the K shell, the N equals 1 shell, alpha referring to the principal line given off of aluminum. And so excitations from aluminum are made from its core energy levels, which gives off X-rays, okay? So if you've seen this before, or if you've heard me say aluminum K alpha, that's an X-ray energy source, typically about 1,400 electron volts worth of energy. So that's a lot. That's a lot of energy. And as you saw from this previous slide, you know, these binding energies of these elements are quite small. So those photoelectrons will come off with a huge amount of kinetic energy, all right? So let's see, what else can we talk about? And then finally, this long rod that you're seeing, that's called a manipulator. And so that's typically where you will place your sample. So you can see in this device, this little hatch would be opened up so you could place your sample on a little robot arm, and that robot arm will close up, seal everything, just like the International Space Station has a load lock and the main chamber, right? The main space station chamber where everybody lives. Well, that's exactly how these types of vacuum systems work. You'll have the load lock, okay, which can be exposed to atmosphere because this detector region will have a valve. It'll have some kind of way of shutting it off, all right? So this can stay under pressure. You place your sample in the load lock, and then now that you pump down the load lock, you open the sample chamber, the whole thing gets pumped down, and now these robot arms will actually move, right? It'll manipulate the sample right into the path of the beam. And that requires really high precision movement, right? To get that sample right in the beam path. So there's just a ton of technology and complication involving XPS. But that makes it pretty awesome, right? So let's get a better look at the hemispherical energy analyzer, okay? So here you can see, this is actually showing you several different photon sources. So the aluminum K alpha is the most common X-ray tube, aluminum K alpha. But if you were doing just regular photoelectron spectroscopy, you could absolutely do a UV lamp. You won't be probing the core electron levels, but you can still do photoelectron spectroscopy on the valence levels with a UV lamp. You could, of course, use a laser, or you could use a synchrotron. And so by synchrotron, that's a particle accelerator, such as LBNL. That stands for Lawrence Berkeley National Laboratory. So Lawrence Berkeley National Laboratory is one of the more famous synchrotrons in the United States. So it's basically a particle accelerator that can make any frequency of light that you want. So there is a lot of really cool XPS studies going on at the particle accelerator floor, where people pump particle accelerator radiation directly into their vacuum chamber to induce photoelectron spectroscopy. Okay, so here you can see photoelectrons are ejected off of the surface, and in this hemispherical energy analyzer, it kind of works much like a mass spectrometer, where it separates electrons based off of their kinetic energy. Now, in a mass spectrometer, everything has a constant velocity, but the mass changes. So that changes the trajectory that those mass ions will have. Well, in photoelectron spectroscopy, all of the electrons have the same mass, right? So what changes with these photoelectrons is their kinetic energy, and thus the speed that they come off the surface, okay? Faster photoelectrons will make it further onto the plate, and slower photoelectrons will make it, closer to the plate of the detector, okay? And so typically these detectors are some type of photomultiplier tube, right? With some way of discriminating where each electron comes from. And that's how it can discriminate the electron's energy. So here is a typical XPS spectra. And so what we see here is there's one source of radiation. So this is typically, so if let's say this was aluminum K alpha, right? I noted that that's 14 eV. So we're only going to have one, monochromatic source of radiation coming off. The hemispherical energy analyzer will scan through all of the various kinetic energies, okay? And as it's scanning through, it will find various peaks corresponding to those quantized electron orbital shells and subshells, okay? So for example, if we look at platinum right here, you can see at very low binding energy, so this electron binding energy is calculated via the following. So we remember the photoelectric effect says kinetic energy of the electron equals h nu, the incident radiation, minus phi, okay? Well, phi is really, as we said, the binding energy. This is what you want to determine, okay? So the h nu, the incident radiation is constant. So by scanning different kinetic energies, right? And knowing that this energy is constant, we can measure the binding energy of various electrons in atoms. Okay, so for example, if we look at platinum, here we can see at a very low binding energy of, let's say like 90 electron volt, we find 4F. Okay, and as we keep scanning into higher binding energies, and keep in mind, right, these that 4F electron, for example, that's going to have the largest kinetic energy, consequently the smallest binding energy. And it makes sense that 4F has the smallest binding energy because it's the furthest away from the nucleus, right? And as we scan across the kinetic energies, we can see here now the appearance of 4D electrons, 4P electrons, right? And you can see those get to higher energies because we're getting deeper down into the core of the atom, all right? So moving on, so we can see this in this Bohr level diagram, photoemission. This creates the primary photoelectron, okay? And so here what we also create is what's known as a hole. So a missing electron from the core level. And we could get pretty hardcore into the quantum mechanics of what we call this hole pair situation. Okay, a hole pair situation is the electron hole that's created as well as the electron pair that relaxes back down into that hole. So we could get crazy hardcore into the quantum with this, but we're not going to worry about that for this class. Okay, and so what can also happen now in the X-ray photoelectron spectroscopy is secondary emission processes. And those secondary emission processes are very much related to this hole pair dynamic. Okay, so for example, you can see that an electron up in this level can relax down. Because that electron at a higher energy level is relaxing down to a lower energy level, that's going to give off some fluorescence, and that's going to be X-ray fluorescence. And this is very much how that aluminum K-alpha source of radiation works. Okay, so this is how we get those X-ray photons in the first place. But now we can have secondary emission of electrons due to the instability created in this process. And those secondary electrons that are emitted are called Auger electrons. It's not Auger, it's the name of a French scientist. So it's an Auger electron emission. And so those Auger electron spectra can also provide lots of diagnostic things about our analytes. However, Auger spectroscopy gets ungodly complicated because you're dealing with all of these secondary effects. So the primary photoelectron is most useful in the characterization of materials. Okay, so let's move on. So here is a closer view of some various elements. And I want to talk about these peak shapes. Okay, so we can see here carbon 1s. And all of these are elements, so there's no, we don't have any molecular structures right here. So this is carbon solid, solid copper, solid silver, solid gold, okay? And so all of these have oxidation states of 0, all right? So carbon always shows up around 285. No matter what kind of carbon it is, the carbon 1s always shows up in the vicinity of 285, okay? And it's one single peak. Because if you recall, carbon is 2s2, 2p2 in its valence shell. I'm going to get a periodic table in front of me here just for backup. And so if you also recall then that 2s2, 2p2, that's going to make a triplet state. But what's important about that triplet state with both of those electrons being spin up or both being spin down, there is no spin-orbit splitting is what we are getting into now, okay? But what about copper? Well, copper, if you recall, its electron configuration should be 4s2, 3d9. But if you recall, what ends up happening with copper is it's 3D10 4S1, and that is a doublet state. And lo and behold, when you excite the copper, in this case 2p, it doesn't really matter that it's coming from 2p. What's important is that copper is a doublet. And so when you eject core electrons from a doublet state, you could be ejecting either a spin-up electron or a spin-down electron, right? Pauling tells us both are possible. And so now something really interesting happens. So you get two peaks, because we know that copper is a doublet, and so the two peaks makes copper a doublet. We can also see that they're well separated. And this value of 19.8 electron volts, that is the spin orbit coupling constant for copper. So in other words, when that electron is spin up and it gets ionized, it's going to have a different binding energy than if that electron were spin down. And so if you recall, the 2p level is split by those J values. So there's going to be the J equals 3/2 and the J equals 1/2. And so we also recall here that in this diagram, ionization would be up here. So you can see the spin down electron, the J 1/2, requires more energy to be ionized than the J 3/2. And if you look on this scale here, you can see, so we would typically, in XPS, we just put the J value next to that. That's how this nomenclature works. So the 2p 3/2 is corresponding to the 2p level electron, but specifically the J 3/2 electron. Okay, and so you can see that J 3/2 is about 93, 900 and maybe 30 electron volt or so, right? But now you can see as we scan across, the 2p 1/2, the spin down electron, definitely has a bigger binding energy, right? And so from the XPS technique, we can calculate now that this spin orbit coupling constant, or in other words, the difference between these energy levels for copper, is 19.8 electron volts. And that's a big difference, that 19.8 EV, okay? So now if we look at silver and get a periodic table in front of you, right, you can see that it goes copper, silver, gold. We recall that silver is also a doublet state. It's going to adopt the same type of configuration as copper, but it's going to be a 4D10 5S1. So silver is also a doublet. And then now here we're looking at the 3D electron level. And so because silver is a doublet, it's going to have spin orbit splitting. But you can see that that spin orbit splitting is much less than it is for copper. And that's due to the fact that silver has a lot more electrons. And so because it has a lot more electrons, that difference of being spin up or spin down is less significant. And you can see when we go to gold, right down the line, gold is also a doublet, 5D10, 6S1. And now we're talking about ionization from a core F level. It also exhibits spin orbit splitting, but not nearly as much as silver and not nearly as much as copper because of the large presence of electrons. And so we also notice now with our J terminology, right? Recall J equals L plus S through L minus S. And so for the 2p level, L was equal to 1. So 1 plus 1/2 gives me 3/2, and 1 minus 1/2 gives me 1/2. But now when we're going to the D level right here, right? Remember L is equal to 2. So that's where we get the 3D 5/2 or the 3D 3/2. And then for the gold, for the F block, right? L is equal to 3. So that's where we get the 7/2 or 5/2. Okay. You also notice the intensity for the upper lying J level is higher, okay? And that has to do with the number of electrons that are in that level. So what you can see from XPS is it actually shows that there are more electrons existing in that upper spin level. And this is a good diagram of why that exists, okay? So recall, and this is getting into why the spin-orbit splitting is observed, okay? So if you recall, we have an electron, remember our right-hand rule, we have an electron orbiting around our nucleus. And via the right-hand rule, that creates angular momentum spinning in the up direction, okay? So not only is this electron revolving around the nucleus, but it is also rotating, It's spinning as it's revolving. And so when that happens, this high J value, okay, so for example, the J equals 3/2, 5/2, or 7/2, you can see that the electron's intrinsic angular momentum is aligned with its orbital angular momentum, okay? Whereas the low J value, they are unaligned, They're anti-parallel. And so that's actually why the low J value has a lower energy and consequently a larger binding energy to remove it, okay? So the binding energy of low J is higher than the high J value. And because of the way those angular momentums are, anti-parallel, that makes that electron stuck to the core a little bit, it's bound a little bit more tight, okay? So the magnitude of the spin-orbit splitting increases with nuclear charge. So I have to think about this. Did I describe that correctly in the past? So magnitude of spin-orbit splitting increases with nuclear charge. Oh, and then, yes, so I'm going to go back and re-explain the copper, silver, gold. I'm sorry. So magnitude of spin-orbit splitting decreases with distance from the nucleus. So there's two competing effects going on here, where technically the larger the charge is, the more this effect is going to be displayed, okay? So the larger that charge is, the tighter that electron can be bound, and thus when you flip it spin up or spin down, the spin-orbit splitting effect is really amplified. However, as we get electrons further and further away from the nucleus, that spin-orbit splitting is less important. So if I go back here, let me explain this again. So if we were looking at all, let's say 2p levels from copper, silver, and gold, then we would see those spin-orbit splittings get bigger as we get on copper, silver, gold, okay? However, we're not looking at all 2p levels, It's 2p, 3d, and then 4f. So this effect here of seeing decreased spin-orbit splitting in these examples is related to the fact that we're getting further away from the nucleus as we look at a 2p or a 3d or a 4f electron level, okay? All the same, what's important about this spin-orbit splitting constant is it is a constant, and it can be used as a diagnostic tool to identify what you have in your sample. So suppose you're analyzing a sample and you don't know what its composition is, So when you get doublet peaks like this in this orientation, that will tell you, okay, I'm looking at a doublet state. And then when you calculate from the peak to peak, so that's all the spin-orbit coupling constant is just the difference between the peak to peak. So for example, if we saw that it was exactly 19.8, we could definitely say we have copper in our sample. Or if we saw the spin-orbit coupling constant of 3.65 with two peaks shaped like this, we could definitely say that it's gold. So that spin-orbit coupling constant is a diagnostic characteristic of various elements. Okay. So I know I've been talking quite a bit. I think I've just got a few more slides on this. I just wanted to do all of this XPS talk in one go. So here's another look of a full photoelectron spectrum in more detail. And let's dissect this, okay? So here you can see at zero binding energy. These are the electrons that are furthest away from the nucleus. So that VB right there stands for valence band. And now what we're also looking at here, you can see this is titanium oxide. So we're actually looking at a molecule. Okay. You can see we're also seeing what the incident radiation was. 730 electron volt would be the incident radiation. So that means the highest energy we could go out to would be just under 730 electron volt. Because with the binding energy of 730 electron volt and an incident radiation of 730 electron volt, we wouldn't have any kinetic energy, right? So everything down here has the highest kinetic energy, right? Consequently, the smallest binding energy. And so now as we scan across, we can see various features corresponding to titanium and oxygen, right? So here is the oxygen 2s, the titanium 3p, the titanium 3s. So here you can see in this region, we see the Auger peaks, okay? And sometimes the Auger peaks can be really well defined, such as this oxygen or titanium, but sometimes they're not so well defined. Actually, excuse me, the oxygen is the only one of these Auger peaks that's really well defined. This carbon 1s right here, this is an XPS peak, okay? So carbon 1s, if you recall, always occurs at about 285. So why would there be carbon in this sample? And the answer is because when you put your sample on the manipulator stage, so right, this is our, I'll just call it the sample stage, right? And here is our analyte, okay? Every now and again, the XPS technique can sample some of the elements on the sample stage if you haven't like manipulated it perfectly, okay? So XPS, as we said, is really, really sensitive. It could also be carbon contamination from someone's fingers, right? So this is a really, really sensitive technique. So here we can see spin orbit splitting from the titanium 2p 3/2 and the titanium 2p 1/2. And just, taking a quick scan at my periodic table right here, we can see that then titanium in the 4+ oxidation state, right? Remember, so this is titanium 4+. So you can see that gives spin orbit splitting in that core level, okay? And so then here you can see we've got the oxygen 1s. So now what I also want to point out is the background shape right here, okay? So the baseline or the background in XPS is quite terrible. And the reason for that is because there's also a lot of stray electrons, secondary electrons, or even tertiary electrons that can also make it to the detector. And those electrons are typically not well defined. They're not coming from quantized levels. And so that gives a lot of background noise, okay? So that's just a really noisy background. And so that's why the process of deconvolution in XPS is really important, because these baselines in XPS are always quite terrible. So let's get a look at chemical shift and oxidation states, okay? So if we were to look at the XP spectra of, let's say, silicone, okay? So you can see it's noted right here. Here is its binding energy, okay? And so this is looking at some of the valence levels. So the valence levels, as you might imagine, are more sensitive to chemical environment. All the same, the core levels are also sensitive to chemical environment. But the reason why I know that this is core levels is because of the really low binding energy that's down here, right? Just a couple of EV. Okay, so here you can see is just silicone, okay? But now what happens as silicon goes through these increasing oxidation states? So for example, a silicon bonded to one fluorine, right? That's an Si plus. And a silicon bonded to two fluorines is an Si2 plus. And then an Si3 plus and an Si4 plus. Okay? Well, so now when you think about it, you're trying to remove an electron from something that's now positively charged, right? So that's going to be harder to remove that electron. And we can see that with all of these various peaks, okay? That they're shifting to higher binding energies as the oxidation state increases, okay? So that's what we've got right here. Generally an increase in oxidation state causing an increase in binding energy. And that's a wonderful diagnostic, again, of what kind of molecules we might have in our spectra. As you can also see, these peak shapes are not great. So once again, the process of deconvolution, as you've seen in the Spec 1 assignment, is really important in XPS. Okay. So now the last thing I'll talk about is looking at a full-on organic molecule in XPS. This can be done. So this is a look at, oh, I forgot to write it down here. I guess this would be some type of polymer. I'm just going to say polymer. Okay. And so you can see it's got various types of oxygens as well as various types of carbons. And so now, again, if we look at this 285 region where carbon always appears, you can now see it's quite dynamic. For example, the carbon-carbon bond shows up around 284.6 eV. And right here you can see that's corresponding to the carbon-carbon bond in this ring. But now you can see that there is a carbon-oxygen bond from the ether, right, that shows up over here. And similarly, this neighboring carbon molecule is even affected. Even 2 positions over from the oxygen, it appears shifted relative to the carbon-carbon bond. So really sensitive to chemical environment. And you can see the carbonyl region right here, also the carbon XPS energy, the binding energy, shows up over here as well. Okay. And then similarly, if you look at the oxygen 1s, so these are both the same, molecule. It's just focusing on the different region. Right, so oxygen always appears around 532. So I'm going to write that down. Oxygen is always around 532 electron volt. Carbon is always around 285 electron volt, for the carbon 1s or the oxygen 1s. And so now, as you can see, there's 2 different types of oxygen in here. Okay, and those have to be deconvoluted. Right, there's the ether oxygen and there's the carbonyl oxygen. And so the diagnostic we use in XPS, again, is recognizing that when I'm talking about triplets or singlets, I only expect 1 peak. But if I see multiple peaks in my XPS, and particularly multiple peaks right on top of each other, that's telling me I have a different chemical environment. That's telling me I have more than 1 kind of oxygen or carbon, for example. However, if I see multiple peaks that are really well split, like these atoms right here for copper, silver, and gold, okay? And particularly seeing these peaks in this ratio, right? Where you can see that the high J value is always slightly higher than the low J value. That's a diagnostic that tells me I'm looking at a doublet state, because those doublet states are typically separated enough that the peaks aren't right on top of each other, okay? So all of these are good diagnostics for XPS. And then the final thing I'll say is, if you were looking at this XPS spectra, and suppose you didn't know this was the organic molecule you were looking at, you would have a really, really hard time assigning all of these different functional groups. So typically, people also use FTIR in tandem with XPS for total analysis. So you see this quite often in literature where someone has taken the XPS of their new and interesting molecule they're trying to synthesize, and they've also done FTIR. The FTIR tells them, what functional groups are present, and then from that, using the FTIR spectra, you can use the XPS spectra to confirm those results And that's what I would call the spectroscopic kill, when you can use two different techniques that help you identify your molecule. That is a for sure way to characterize everything you want to know about your molecule. Okay, folks, that's all I'm going to say about XPS. The next 2 or 3 lectures or so will be on techniques in UV-Vis spectroscopy. See you in the next video.